Calvin talking next. Calvin
It's my pleasure to introduce Cal Bartholomew, our next speaker. His work has been well cited by previous speakers this morning. And in addition to his research productivity and catalyst deactivation, he's pioneered many of the studies in Fischer-Tropsch. And today he's going to talk to us about a microkinetic model for iron-based Fischer-Tropsch catalysts. So, Cal.
Thank you. I'm going to talk about something different than in my abstract, and apologize for that, but we didn't get the iron work done, but it turns out that Jim Domestic and some of Manos Mavrocortis' students got to work and came up with a microkinetic model for cobalt. By the way, there's still a couple of seats up here for those of you who are standing in the back. Anyway, we decided to go with the cobalt, and we finished some of those calculations late last night. Just a little background here. You all know that Fischer-Tropsch synthesis is very important. It's being commercialized, and now we see the development of a GTL industry. And there have been many improvements to the technology, but these depend to a great extent on our ability to develop accurate, comprehensive reactor and kinetic models. And we know that rates and reactant product compositions vary over at least an order of magnitude in a commercial reactor. And so we can have rates varying 10 to 20-fold and hydrogen to CO ratios even up to 100. Now the microkinetics models, which I'll call MKMs, or Langmuir-Hinchelwood models, LHMS, are really needed for reliable prediction of the rates over a full range of conditions. Now the MKMs, the microkinetic models, are the very best way to go because they will give you the very best picture over a wide range of conditions. However, given their large computational requirements, some modelers will still insist that they want to use a Langmuir-Hinchelwood model. And in fact, the Langmuir-Hinchelwood models are very useful for preliminary design and also for student problems. And so this is one of the reasons that we would want to perhaps develop Langmuir-Hinchelwood models as well as microkinetic models. Now, just a little background here. There have been more than a dozen previous macrokinetic studies, and each of them, interestingly, covers a different range, but it's always a relatively small range of conditions. And the power law and Langmuir-Hinchelwood rate expressions that have been reported in many of the previous studies may not be statistically valid since too many parameters were fitted by too few data. So statistically, they're not on a strong foundation. Two microkinetics models for FTS on cobalt were reported previously, but they have limited application and they haven't been validated with representative sets of data. Now the use of kinetic thermal parameters from microkinetics models in building rate laws has been limited, and as far as I know, hasn't been done for cobalt. Now, the issues I'd like to address in this talk First of all, what is a viable approach to building a microkinetics model? And I should mention here right now that we have been collaborating with Jim Domesic and Manos Mavroukakis at the University of Wisconsin-Madison, and we are working on this iron project, but we're also collaborating too on the cobalt that I'm presenting here. And how can we use then microkinetics models to develop better rate expressions, and what factors limit the validity of the previously reported rate laws, and how can they be overcome? Well, to answer the first question, to develop a good microkinetic model, you need a lot of data, and you need some good theoretical foundation as well. You need detailed activity, selectivity, stability data that will be used to validate the model. And of course, you need to do your best to look at some of the surface intermediates and the catalyst morphology, do adsorption, microcalorimetry to get heats of adsorption, XPS, XRD and Mossbauer to look at the oxidation states of the bulk in the surface, and of course DFT and theoretical methods that will allow you to get a fix on the various kinds of species. Well, Manos Mavroukakis did a great job of showing us what can be done with DFT. And of course, isotopic studies, such as Sitka, that Jim Goodwin talked about earlier today, are very useful. So putting this all together, we can come up with surface reaction schemes and kinetic models that can be used then in comprehensive reactor and plant models for FTS in GTL plants, and greatly improve what we're doing. Now, what kind of information do we get from an MKM or microkinetics model? Kinetic parameters, of course, for each of the elementary steps, as Professor Mavroukakis showed you. And site requirements, which he also showed you, and predictions of rate over a wide range of conditions from the solution of the differential equations based on those kinetic parameters. Now here's the microkinetics model that I've been referring to, that was developed at Wisconsin. And you can see it consists of 17 elementary steps up to the formation of C3 hydrocarbons. And you have your heats of reaction, equilibrium constants, and your pre-exponential factors, either for the forward or reverse steps here. So you have all of the information that you need to describe this reaction on a cobalt 001 surface. Of course, as Professor Mavroukakis pointed out, a step surface will probably be more representative of a commercial catalyst, so maybe that will be the next one to look at. But at any rate, that's some of the parameters. Now, the site requirements were presented by Gakole and Mavroukakis at the ACS meeting, and they showed that you have different site requirements for iron 110 and cobalt 001 for the different species that absorb on the surface, and they might include 3 or 4-fold sites, or what we call long bridge, or FCC, RHC sites. And I think that Professor Mavroukakis did a great job of showing you the transitions and the role of these different sites. And so when we model a reaction like this, we really need to take into account that there are different kinds of sites that are involved. Now, I turn to the work of George Huber. You may have noticed that George was listed twice once for BYU, once for University of Wisconsin. He did masters with me, and as part of his work, he did a kinetic study. Then he went to Wisconsin, and he's been working with Jim Domesic and done a lot of interesting stuff, but he also has helped me last night, matter of fact, put together the calculations. But this is a set of data that George got back in the year 2000. You know, we never published or really widely presented this because there were some problems, and we'll talk about that. Not that we didn't do things the right way. We did a very nice statistical design of the experiments, and we got data, 20 atmospheres, 200 degrees centigrade. You notice we have 8 conditions there where we repeat them, and our runs are in a random order, and we cover a fairly good range of partial pressures of CO and hydrogen and even water. And so we get these rates and these methane selectivities, and this was on a cobalt platinum silica catalyst. Well, based on this, we went to the literature, looked at various rate expressions, and we looked at this rate expression by Sarup and Wachowski and Atkin and Onsen. This appeared to be one of the better rate expressions that we looked at. We looked at probably a dozen of them, and we used data from half a dozen studies. And our approach was to determine orders for PCO and P hydrogen, assuming that A and B are the only 2 significant constants. So in other words, we went to a 2-constant Langer-Hinchelwood expression like this. And this is the one I'm talking about. Our assumptions are that hydrogenation of carbon and formation of water from OH plus H are the rate determining steps. And the most abundant surface intermediate is surface carbon. Well, we fitted the data to this and other models. I think this was the first model, could be the second one, but and then the power law, and then we looked at a Yates and Satterfield model. And what you see is that you get a fairly good agreement between the calculated and measured rates. And in fact, when you look at the normalized standard squared errors, which is a good measure in principle of how well the data are fit, we get these kinds of values, which are really good, and suggested that we were getting a very good fit of the data. And we looked at the normalized deviations from the average value, and they were less than about 5%. So it seems to be working pretty well. We seem to have a pretty good fit. Except now George went to Wisconsin. He took his advanced statistics class, and they learned how to use this statistical package to do a nonlinear regression. You know, this is something most of us, I guess, haven't done. I hadn't done it. And when he did this, he correlated the A and the B parameters on this plot here. And the result of the linear regression was this ellipsoid here. And what you see is that B can vary anywhere from about 0 up to 2, and A can vary anywhere from 0 to 200. In other words, we haven't really specified the variables. In fact, this is how well we know A and B. Now that was kind of a shock when I heard this from George. So the conclusion was A and B, or small a and B, in the rate equation can't be specified using a typical statistical approach. So, this is a can of worms, isn't it? Well, what's the solution to the dilemma? Use MKM to specify all the variables, except one. And then you can use that to fit the data. And use a nonlinear regression then to determine the unspecified parameter. And so this is what we did using now this new microkinetic model from the University of Wisconsin. What we did then was to fit the data, but as we were going through this process, we realized that these data here for the cobalt 0001 surface, which is flat basal plane, that these data have a different rate determining step than the one that we predicted, which was carbon hydrogenation. And so this posed a little bit of difficulty. So we did a little bit of a fix here, and we assumed that for the numerator, we assumed that the rate determining step was still carbon hydrogenation, but that the most abundant surface intermediate is carbon monoxide, because CO dissociation is, after all, 2, and the chi-square distribution probability is 1. So we have a very good fit of the data. In fact, it's excellent. Similarly, we took the data from another study that was done in our laboratory by Zanaro, Roberto Zanaro, and we have then calculated TOF versus experimental TOF. Again, we have a very good chi-squared and a good chi-distribution probability. I must insert the caveat that we threw out some outliers, and I think that that's probably necessary in doing this kind of treatment. In conclusion then, we have a dilemma, and I think it's a dilemma for the whole catalyst community and for all of the kinetic studies and the fitting of data that we have been doing. And that is that the typical approach to fitting kinetic data to a Langer-Hinshelwood expression could lead to highly correlated constants. And the standard errors are large, as I showed you, and the result is that the constants are really not specified. The solution is to use constants from theory or microkinetics modeling to specify all but one constant, which then can be fitted by nonlinear regression. And the other thing we learned by doing this is that for the cobalt 0001 surface, CO dissociation is rate determining and CO is MOSI, whereas on a step surface, I would like to propose that maybe carbon plus hydrogen could be the rate determining step. I want to thank members of my research group that have been a great help to us on this project and many others. They're a fun bunch to work with. And also I want to thank you for listening.
We have time for a few questions. Yeah, Jim.
Yeah, Kyle, interesting work. When you talk about say using the theoretical work that Domestic and Mike did, and then fixing all but one, do you have enough to say choose different parameters to fit to leave as a variable and to try fitting to the experimental?
Yes, you do have that choice.
Because that would seem to give you better proof if you go different routes and come up with the same parameters. Right?
Yes. And what I'm told by Jim Domestic's students and by Jim is that this is the way they go about it. They'll look at various scenarios to make sure that there's a self-consistency in the approach. But I think we have seen from the work that's been published by Domesik and some of his former students and a lot of other groups now that are doing this really fine work, like the group in Denmark, we find that you get very good agreement with commercial data. For example, the work that was done on the ammonia synthesis. So I really think that these models are the wave of the future. And you know, we need to develop more of them and incorporate them into our modeling of reactors and processes.
Hans, first I'll get you in second, Alex.
I wonder whether the basic assumptions of the clean surfaces, yes, the clean iron and the clean cobalt surfaces, so if we can finally stick on those, because we on the other hand know that the surface is roughened of the cobalt catalyst during the synthesis, and the iron forms the carbide and the potassium on it. So I feel the real situation is much more complicated. Even you get very nice results, excellent relationships and equations.
Yes.
Nevertheless, somehow the reality seems to be more complicated.
Hans, you're absolutely right that the real catalyst is much more complicated, but you notice that in Professor Mavrakakis' presentation, he starts with a clean surface, then he adds some subsurface carbon. And then, you know, and then he adds a platinum promoter. That's what we plan to do in this joint study that we're working on. And we will try to do the same thing in our experimental work at BYU to complement that, including the isotopic studies. We'll do clean iron or, you know, unpromoted iron, and then we'll do the supported and promoted and so forth.
Yeah, Alex, last question.
Cal, I'd like to make two observations. First of all, on that list of rate parameters you have, I believe those were all predicted on an empty cobalt 0001 surface. But under reaction conditions, as you yourself state, you have a lot of CO on the surface. You have a modest amount of carbon. The local parameters change as a result of the nearest neighbor occupancy.
Yes.
And that has to be taken into account when you do the Monte Carlo simulation.
Right.
So that's not yet at the level that you're discussing.
We're not quite there yet.
The other observation is that the data range in which you're making the comparison is only a factor of 3, from 20 to 60
Yes.
units. And that's too narrow to get anything truly meaningful that you want to test.
You're very astute, and that is the case. And of course, we have plans to cover a wider range and get more sophisticated models for fitting these data. And that needs to be done. But it's a start.
Thank you very much.